Hey everybody. Sorry we were cut off at the end of my solution to this exercise. Somebody had the nerve to come in and tell me to get out of the classroom just because they had a class scheduled. The nerve is, no, just kidding. Anyway, here's where we left last time. And about all I can really do is manipulate this a little bit. I'll divide both sides by the absolute value of x, and then use the fact that the product of absolute values is the absolute value of the product. And we have the absolute value of something equal a constant. Well, I guess that can only happen if the expression inside is equal to a constant. So this is our solution. And you know the initial condition that we had? Maybe the person who interrupted me before I could finish this exercise did me a favor, because the initial condition that I had, I don't know where I got it, but it had absolutely no relevance to the exercise I was working on. So whatever the initial condition was, just throw it in the wastebasket because that's where it belongs. We'll do another transformation of variables problem. This exercise used the classic method, the classic substitution. That is v equals y over x. There are other substitutions that we can use. This is just the classic substitution when we have a homogeneous differential equation. And when I say that, I'm saying we have a differential equation that can be written in this form. This is a homogeneous differential equation. If we make this substitution into that equation, then the new equation can always be separated. The variables can always be separated. So this is a classic substitution in the sense that it applies to homogeneous differential equations, equations that can be put in this form. The substitution of variables that I'm about to use next doesn't apply to a homogeneous equation, but it does allow us to transform an equation in which the variables can't be separated into one in which the variables can be separated. So let's look at that. Let's take a look at this one. I don't think I can separate the x's and the y's. And I don't think I can write this in the form of y prime equals f of y over x. So let me use a different substitution. And here's what I'm thinking. I want to take the contents of this radical and write it as a perfect square so that the radical and the perfect square will undo each other and I'll get rid of the square root. So here's what I'm thinking. I'm thinking of taking the contents of the radical and letting that be equal to v squared. Having done that, I'm going to have a need for replacing not just y, but dy dx also. So I'm going to compute the derivative of both sides with respect to x and hope that things look good. Derivative of v squared with respect to x, I get 2v times the derivative of v with respect to x. Remember, these two variables are different, so not only do we look at v as a variable, we look at it as a function of x. So this is a function raised to a power. So we have the power rule as usual, then we have to multiply by the derivative of the function because of the chain rule. Now let's move over here. Derivative of 2x with respect to x, that's just 2. Derivative of 3 times y with respect to x, that's 3 times the derivative of y with respect to x, which is dy dx. And now somehow I got to get rid of this dy dx and replace it with something in terms of x's and v's. And here's what catches my eye. This thing, well, I have a y prime there, but what I really mean in an equation that has x's and y's, when I say y prime, what I really mean is dy dx. That's what this is. So dy dx, that's square root of 2x plus 3y. And I'm going to make that substitution, and I'll tell you why. Dy dx, that's this thing. Look at the contents of the radical, 2x plus 3y. That's v squared. So I'm going to write this again. Square root of v squared. Technically, that's not v. Square root of v squared is the absolute value of v. But x plus y, x and y are both positive. If x and y are both greater than 0, 3x plus 2y is greater than 0. And that means that v squared, which is this thing, v squared is 2x plus 3y. Well, I'll tell you what. The square root of something positive is going to be positive. Square root of v squared is just v. Now, can I separate this thing? I think I can I? Yeah. I can just divide both sides by 2 plus 3v. Okay. And then I'll just multiply by dx, right? Let me just take a look at that and make sure I like what I have. Yep, I like it. And my variables are separated, so I can integrate. Okay, here's where we're at. And I'm going to rewrite this Oh, holy smokes, what have I gotten myself into? I'm integrating the quotient of polynomials, and the degree of the numerator is the same as the degree of the denominator. Son of a gun. I'm going to have to do polynomial long division to write this in a form that can be integrated. Let's see, I am dividing 2v by 3v plus 2. And I look at the leading terms of both polynomials. 3v goes into 2v 2/3 times. 2/3 times 3 is 2v. I'm sorry. 2/3 times 3v is 2v. 2/3 times 2 is 4/3. And I subtract, I get negative 4/3. So here's what I have. I'm dividing 4/3 by 3v over 2, negative 4/3. And so I'll write that as 4/3 divided by 3v plus 2. Negative 4/3 over 3v plus 2 times 3v plus 2 is negative 4/3. Okay, everything's balanced. And I'll write down my result. For future reference, this expression 2v over 3v plus 2 turns out to be this when we do polynomial long division. Back to our integration. This thing is 2/3 minus 4/3 times 1 over 3v plus 2 dv, and that's equal to the integral of dx, or 1 times dx. This gives us the integral of 2/3 dv minus 4/3 the integral of 1 over 3v plus 2 dv, and the integral of 1 dx. Cool. This thing, we'll call that 1 over u, where u is 3v plus 2. du dv is 3. du is 3 dv. And if we divide by 3, we have 1/3 du is equal to dv. So this is 1 over u. This is 1/3 du. Goodness gracious. Maybe we can actually integrate now. Okay, this is it. We really can integrate now. We get 2/3 v minus 4/9 natural log of u equals x plus some constant. Now, what was u? U was 3v plus 2. And we will assume that v is positive. As our author frequently does. Okay, what do I have to do now? I just have to rewrite everything in terms of x and y. I don't have v, but I do, I don't have v squared, but I do have v. 2/3 v, that's the square root of v squared, which is 2x plus 3y. Minus 4/9 natural log of 3v. And again, v is the square root of 2x plus 3y. Now, let me just take a moment to look over the results before I say that I'm done. Yeah, I guess about the only thing I could do to make it a little bit more sightly is just multiply both sides by 9. Whoops. Multiply both sides by 9. There we go. Okay, did I do anything I should be ashamed of? Probably. Yep, I think that's got it. This is our solution. And as sometimes happens with differential equations, the solution of the differential equation, which is y, is given implicitly as a function of x. So the solution is y, but that solution is given implicitly as a function of x by this equation. Okay, here's another homogeneous equation, and I think it will be pretty easy to solve using the standard substitution. Let's take a look. Remember what my strategy is. I want to get this side looking like f of y over x. That's what I want this to look like. So I think if I divide top and bottom by x cubed, that'll do it. Because I'll have y cubed over x cubed here. I'll have 1 over x squared and y squared over x. Yeah, that'll work. Divide top and bottom by x cubed. I'll have y cubed over x cubed. And I'll have y squared over x squared. And there it is. This is my function f of y over x. So now we make the standard substitution. But we also have to make a substitution for dy dx. Here's the substitution for y over x. And notice we can rewrite this as y equals vx. And if we differentiate both sides with respect to x, here's what we get. Dy dx and remember, this is a product. So we'll get the first times derivative of the second, excuse me, plus the second times derivative of the first, and there's our substitution for dy dx. First, we substitute for dy dx. That's this thing. V plus x dv dx. And then for y over x, we substitute v. Okay. I'll tell you what I'm thinking. I'm going to simplify this first. Yeah, I guess I just subtract v from both sides now. And from this, I can see that the variables can clearly be separated. Multiply both sides by v squared. And divide both sides by x. And multiply both sides by dx. Variables are separated. And again, I assume that x and y were greater than 0, so I can trash the absolute value bars. I beg your pardon. I see something here that's very offensive. The integral sign and the differential work as one, so when we integrate, that differential vanishes. I apologize. V cubed, that's y over x over 3. And what do I do now? Just multiply both sides by x cubed. Yeah, this can be solved explicitly for y, so let's do that. Multiply both sides by x cubed. And just take the cube root. Ooh, you know what? You know what? Let me back up a bit. Let me back up a bit. Let me start from here, and I'll just take the cube root of both sides. See, I did say I was going to take the cube root of both sides, didn't I? Okay. Now I have the square of the cube root of both sides. And multiply by x. Voila.